Chin Woo needs me. I'll drop everything. He needs UW Badger? I'm on it. Are you a UW Badger?
Not right now. Manti just turned me on to the hottest dating site on the internet.
He's not a UW Badger. Are you a UW Badger? He's not a UW Badger. Now that the easy work's over, off to Chin's class.
Are you UW Badger?
Yes.
Ah, yeah, we found one.
Now that we've found UW Badger, here's Chin's problem. He wants to make big bucks, so he's designing a rain catch basin to water his plants and feed into a bird bath. The plants are the most important, so he does a calculation for this first. The pipe that runs to the plants is 50 meters. The height of the water is 25 centimeters. The velocity of the water can be no greater than 2.5 meters per second. He wants to test this by getting a reading at 35 seconds. The area of the basin is large, so the height remains constant. So here's the equation we use to solve this problem. dV over dt, which is the change in velocity over the change in time, is equal to 1 over the length times the gravitational constant times the height of the water minus velocity squared over 2. To run this equation, we had a start time of 0, an end time of 60 seconds or 1 minute, a time step of 2 seconds, gravitational constant of 9.8 meters per second squared, height of 25 centimeters, which will remain constant because the basin is so big, and a length of the pipe of 50 meters. Since UW Badgers were lucky enough to take Chin Woo's 291 class, we can plug this equation into MATLAB using Chin's overall code that he gave us in class. And in this part of the code here, it is a script to set up all the variables to run a function. Solve for this using 3 different methods, both the Euler, the predictor corrector, and run cutoff, just solving the equation using ysolve. So we set up variables here. We have our t-min, our t-max, our dt, and our y initial. Put in our equation in from the previous slide into here and set up our ysolve t. And then using a function that we'll show you in a little bit, it'll solve this using all 3 methods. And here's the function that we set up to run the code that'll and we have the variables t for time and y in this case is the velocity. And we have our output as y, which is the 4, and we plugged into this area here.
The first method we used was Euler's method. Euler's method is one of the oldest and easiest ways to solve a differential equation. First off, we set our conditions from 0 to 60 seconds with a time step of 2 seconds. So our initial velocity is 0, and we ran a for loop through using Euler's method, taking our initial ye, or our velocity, and adding on our time step, timesing through the function f. The Euler's method is a quick and easy way to find instantaneous solutions of your function, but falls short with more complicated equations. This method serves as the building block for other more complicated methods.
The predictor corrector method builds off of Euler's method to come up with a more accurate approximation of the differential equation. Using a for loop, we can loop through our interval calculating different velocities. First, the predictor corrector calculates a rough approximation of the desired quantity by taking the initial condition and adding that to the quantity of the function evaluated at tv of I and the initial condition, and multiplying that by the time step dt. The predictor corrector method then takes that rough approximation and corrects it. The corrected quantity is calculated by taking the initial condition and adding that to the quantity of the function evaluated at tv of I and the initial condition, and multiplying that by the time step over 2, and then adding the function evaluated at tv of I plus 1 and the value from the first step. This is then repeated for all the values over our interval.
Our final method is the run kata method. This takes variables from the previous two methods and corrects for them. And since it is ODE 45, it runs to the fourth order, which means that this will give us the most accurate value for our solution. The final part of our code is plotting the data to compare with each other to see what our solution would be with each of the methods. The first plot here is just plotting all the data and all the solutions, which includes our analytical solution, which just plugs the equation solver. And the second is an error comparison method, where it plots each of the errors of the methods to the analytical solution. So solutions to compare the different methods and see what our final answer would be. As you can see here, at 35 seconds, the velocity was 1.438 meters per second. This is less than the value that Chin had asked for coming into his plants at the maximum, so we're in a good position. Here's our plot of errors for the different methods. Notice how the scale is very small here at 10 to the negative third, so all the methods are pretty similar. But as you can see here, Euler's method is the least accurate, and all the other methods range in basically the same area. For the second part of the design, Chin wanted to install a drain to feed into a bird bath that was draining at 15 millimeters per second. And he didn't want the velocity going to the garden to go below 1. So we put in our T, and he also wanted to evaluate at T max of 3 minutes, so we plugged in 180 seconds for our value. He also wanted a time step of 10 seconds, so put that in here. And then our Y initial, the value started at 60 seconds, so we took our T initial at the velocity at 60 seconds from the previous equation. So the changes we made to the code started here, and we subtracted from the plant velocity the 15 millimeters per second, which converted here. And this will solve for our velocity going to the plants, even with the drainage system installed. This equation will also be called F2 in further slides because the initial code was F regular. The function we ran to make the graphs run, as you can see here, as we said, F2 is the equation used, and everything stayed the same other than taking out the 15 millimeters per second velocity that the drain will slow the velocity down to. So once again, we plotted the data of the 3 different methods and our analytical solution. You can see here the data goes up originally for the increased amount of time and then comes back down once the drainage starts to kick in. The value that we had at 3 minutes was 2.107, which is larger than the minimum value of 1 meter per second that we wanted. So, yeah, it worked. So we compared the error for this time only 2 of the methods versus our analytical solution. As you can see here, the values are a bit larger, and this is because of our time step of 10. So the conclusions that we have from this are that we should use it for more accurate data and go with predictor corrector or run kata from now on to do calculations such as this.
Oh yes, this is powerful stuff. Got me circling like the moon round the sun.